will just briefly mention some work. Actually, it's mainly the work of with undergraduate students, maybe a little bit of work with my other colleague, Yang Liu in China. But I think you guys are talking about, when I look at these conference organization list, even though I couldn't attend the early talks, most of the talks are about prime graphs. So I will not define the prime graph again. So roughly speaking, the prime graph is the element order you have. If you have an element of order PQ, then you have a line connected to it, otherwise you don't. Of course, there are a lot of variations of this. You could define conjugacy class size version and character degree version, and maybe some other group invariant. You can define this, and people have studied other subjects. So this is mainly about the element order version of prime graphs. So I'm a director of the REU at Texas State University. It's a research experience for undergraduate students. Of course, some early work by Thomas Keller. So there is a paper in 2000, if I see that, 15, Journal of Algebra. This is a very interesting paper. So this is, I would just tell you the Grumber, Alexander, and then Thomas Keller. And I think I got the name, because this is the first name, Alexander Grumber, and then a few other people. And they name the paper is a characterization of prime graphs of solvable groups. So I think people have studied this graphs in many different perspectives. I think the early talks, most of the talks are about this, to recognizing simple group using this graph. And of course, this one seems to be in a different direction. They kind of say, okay, what can we say about if we just restrict ourselves to solvable group, what can we say? And again, this is if you look at these authors, I mean, actually, 3 of the authors are undergraduate students. Of course, Thomas Keller is a senior faculty member here. And of course, Mark Lewis is also a senior faculty who work a lot on the prime bar graph of the character degree set. And now, of course, when they start this project, they don't know which direction they go. So it's like, because you can, so the question is, what can you say about all the prime graphs of solvable group? Is there a good description? I think one of the key results, I mean, there are a lot of results in this paper, but I think there is a major one. So let's see what it is. But yes, so here is the main result, one of the main results, okay, in that paper, which I think is pretty nice, says the following, that an unlabeled graph of the unlabeled graph, so isomorphic to a prime graph. Actually, I mean, they just want to be more precise, of some solvable group if and only if its complement they call it well, yeah, this F give it a name, a prime graph, they call it F of some solvable group if and only if its complement F bars of the complement graph is very easy. Just look at the complete graph and then you delete the original graph and you get the complement that is three colorable and triangular free. So this kind of triangular free seems to appear a lot. But I think what's nice is about these three colorables. This is in graph theory called chromic number, I guess. I mean, maybe I don't say it correctly. But of course, at the first glance, you see, okay, this is an if and only if statement. It seems to be nice, but if you think about it a little bit, it's not really a one-to-one correspondence. Here's the if you think about it, so we have, let's say, the prime graph, or maybe the complement are the same. I mean, you have a set of prime graphs, all the possible prime graphs of all solvable groups, right? They have, or maybe I should say, that satisfy this condition. So if you think about it, maybe I should say all solvable groups. And here is the graphs that satisfy those conditions, namely that the complement is three colorable and triangular free, right? But it's not a, you see, it's if and only, but it's not a one. Why? Because when you could have two different solvable groups that map to the same graph that satisfy the same condition. Okay. So it's not, technically, it's not a function. I mean, it's a nice way, but if you think about it, it's a nice way to characterize those graphs. But so I will not go into detail about the proof, but if you think what's the key point of this proof? I mean, the paper is, well, let me just tell you, other than this, what do they study is that they also introduce the concept of the minimum prime graph. So what is a minimum prime graph? So let me go back to the proof. So after I introduce the minimum prime graph, so it's very intuitive speaking, it's very simple. You just say you have a, if you have a graph that is a prime graph, so minimum prime graph of a solvable group, roughly speaking, that by deleting any edge, it will not be a prime graph of a solvable group anymore. So this is how they call it prime graphs. This is very natural. So you see that the minimum means you have a group that is a prime graph of some solvable group. You delete any edge, it won't be realized by any other solvable group. So, of course, for this type of problem, you can study it from different point of view. You can say, what would be the graph theory criteria of those minimal prime graph? I think this paper says something along this line. And all right, but I think there's a minor typo in this paper, but I think they kind of noticed it and fixed it. Maybe they announced it somewhere else, I don't know. But let's go back to this this result. I think this result that is more interesting from the group theory point of view is this one, because what is the main technique? So if you think about why that element is not will not be realized in solvable groups. So roughly speaking, if you have element of order P, so we have a cyclic group of the, let me say, dp direct product with dq, so pqr primes. Of course, clearly, if you have this type of group structure, then you know that you have element of order pq. There will be a line. So if you think about the complement graph, so if somehow that in the prime graph that 2 points are not connected, oftentimes what will happen is you have a Frobenius group. So I think people, I guess, you are familiar with these Frobenius and 2 Frobenius. This group theorists know this very well. Frobenius probably roughly means you have this type of action. You have px on q, and then they have a kernel like this, and 2 Frobenius, and they have fixed point free automorphism. When you have look at this action, 2 Frobenius just means you have px on q, and then you have qx on p. I mean, I'm not saying it's exactly, but what I really means is that it's a vector space that has this p as a characteristic. So, for example, what is a good example of 2 Frobenius? If you look at S4, it's already a good example of 2 Frobenius because you have 2 groups x on a 3 group, and the 3 group you x on d2 cross d2. So this is, and the action here is fixed point free, and 3x on d2. So this is S4 structure, and this is a 2 Frobenius group, and that's kind of tell you that these kind of structure, if you have this kind of structure, you don't have element of order PQ. So, but now you see that why would you end up have like 3 colorable? Well, I guess from the group theory point of view, because there's no 3 Frobenius group, because you kind of can prove that you cannot have this px on q, qx on p, and px on q. Again, this will not happen. So I guess more or less you can see that. And then of course there are a lot of details there. But so on one side you say that all these groups satisfy these. All the solvable group will have. The graphs will be look like this. But then it said if and only if you have to go back, right? So, but and then how this way is you use these kind of group theory property to prove this direction. If you have solvable group, then you have graphs that satisfy these conditions. Of course, you have to go back. So when you go back, that says any graphs that look like this can be realized by some solvable group, right? But because otherwise it's not if and only if. And in order to prove this direction, you have to use construction. You just say, okay, you look at any graph that satisfies those 2 conditions, you can always construct some solvable group that that has this graph as a prime graph. So then they go both directions. Of course, as I said, you could have many different solvable groups be realized in the same prime graph, but here you just need to find one. You just say, okay, I can always find one that can be realized by a particular graph in this set. Okay, of course, in this construction, it's not either. You have to use some number theory that Dixon's theorem, like you can, especially in these type of thing, Pn, if you have like P1 minus n, P2, n minus 1, and so on, you will have enough prime divisors of this multiplication. You can in this, if you have good enough, you can always find many different prime divisors. So that's how it works. But of course, the proof is pretty complicated. You have to read it carefully. I don't think I can present in 20 minutes. So, but okay. Now this is the main result of this paper, part of the main result. Of course, this idea is kind of new, using these. I mean, people think, okay, this is nice because even though it's not a one-to-one correspondence, at least it's an if and only if statement, find a connection between all the prime graphs, I mean, all the solvable groups and the graphs that satisfy certain conditions. It's kind of nice because it bridges two different areas from graph theory and group theory. But so then later people have studied different versions. So I will just mention that Adolphi and somebody else studied the conjugacy class version, size version. I forgot. I mean, if you look at the math sign and you look at the citation of this one, you should be able to see this one, because I think they just borrow this idea here, and they ask if you have conjugacy class size prime graph, what can you do? And they also have a characterization. I think, if I remember correctly, it's the complement of that is triangular free and two colorable. It's just like bipartite. So anyway, so this is on the side track. Now, of course, later, Thomas and I are mentoring another team of REU students. It's in 2020. So that paper is new. This paper, let's see. Again, this paper are mainly written by undergraduate students. It's kind of amazed. I think Chris Flores and Jonathan Higgins, Kyle Hong, Thomas Keller, many authors. So David Shen and myself. Yeah, I only contribute a little bit in this paper, but I think the main work was done by this student, David Shen. But I think the idea was, what should we ask if you go a little bit? Of course, in this early paper, the solvable case has been characterized. So I think Thomas had the idea. I mean, you've done for solvable case, and we can go two directions. You can say, okay, what can we say that if it's a little bit bigger than solvable groups? This is some recent work, like last year, 2021, 2022. Thomas, it's mainly Thomas working with his other groups of students, expand the solvable case to include some simple group. I think what they did is they say, what if they have A5 is a composition factor, or like simple groups with just 3 different primes. These are limited, right? So simple groups with only 3 different prime divisors, I guess. So they try to extend a little bit along this direction, but it turns out that this is very hard. To look at the paper, they already posted on arXiv. Even though dealing with A5 cost, I think I worked on this a little bit. I use Gap to help them to calculate some property of this representation of A5, but even though just including A5, that's a lot of work. I mean, even like, and then later they add all the simple groups of 3 different prime divisors. This paper is like 30 pages long. It's kind of crazy. I don't know. I mean, I haven't read this yet. I worked a little bit on this paper, but not this one. But so even though you go a little bit further, seems to be hard. Of course, you would hope that you will add all the simple groups in. I guess he told me it's really impossible. But the 2020 paper is like you go backwards. Say like, what if I go a little bit smaller than solvable group, right? Because of course, inside solvable group you have neopotent group. I mean, neopotent group maybe that's too small, but maybe you can say a little bit bigger than neopotent. How about neopotent by neopotent? And we do get some result along these lines. Of course, I mean, this paper is also long, but I would just pick a most interesting one. And I would tell you what we did is that you have this result here. So as a theorem, 1.1 in this paper says, let G be a meta neopotent. The meta neopotent just means you have two levels. You have a normal subgroup with a neopotent, and the quotient is neopotent. It's kind of very simple. You just get two, because an arbitrary solvable group you can have fitting height arbitrary long, but neopotent is like you have fitting length just two. And F is its prime graph. Then we know that the complement is bipartite. So of course you kind of see this direction because we know that in general that in the previous statement it's three colorable. Three colorable just means that the chromic number is 3, but bipartite means chromic number is 2. So you see that the motivation is if you reduce a group structure from arbitrary solvable, when will you get the bipartite? Of course, there are different layers. There are other layers like this. You can talk about square free order of a group which is square free, which is a little bit smaller, right? So square free order is smaller than the I guess I don't want to say it's wrong, so let me double check. So yeah, I guess that's correct. And the other part is that if F is a graph such that the F complement is bipartite, then there exists a group of square free order whose prime graph is isomorphic to F. All right, so but if you think about this, so what you really get is that you do have a nice criteria, because if you look at all the meta nilpotent group, if you look at this set, then you have a if and only if kind of the same as the previous result. Any meta nilpotent group will be a set of graphs that F prime is bipartite. So then, and then of course, if you want to go back, of course, you can say it's like that, but then you wouldn't go too small, because as long as this this group is a meta nilpotent, but then you have a subset of it, which is called the square free. So if you say that if you think about the class of groups, right? So you have solvable, and you have meta nilpotent. Sorry, nilpotent is a subset of that. So it's a subset of subclass of that, and then group of square free order. even is a subset of meta-nilpotent. So you would say any class in between will have any classes in between these two will have this if and only if statement to this set of graphs, right? Because if you go too small, then you will not find a pre-image of that one, because that if you have this, it will be realized by this. So what we have here is any class, any subclass of solvable groups which is in between, you have the same characterization of this. Right, this is kind of interesting. Of course, in that paper, they also studied other property of prime graphs, like if you have and this is only a half, I mean, maybe a small, I mean, a portion of this paper, but they also talk about the nth power free, or I mean, this is a little bit bigger, or the cube free order and so on. Yeah. So the nth free power is a little bit complicated. And I think in this paper, they already started to including A5, but they didn't do too much along this line. So, but that one was completed later in the last 2 years with other undergraduate students. All right, so now I want to say a little bit work that I've done with Liu. So of course, we have this result of characterization of solvable group. So Liu and I says, okay, we have characterization of solvable group, meta-nilpotent group, and some other family of solvable groups. So we kind of are interested in co-degree. So the co-degree is some character theory defined by Chen. So the co-degree is very simple. You just look at chi1 over, I think I forgot what's the definition. Sorry. It's a kernel. Yeah, it's like, yes. So usually you see you have, so if you have character, that's a character theory. So the co-degree is defined to be, you have G. So I think they have two versions. First, people said, okay, how about this? Just the order of the group divided by the, but then Chen realized this is not the right definition, because if you define things this way, you don't have rich properties. I think Chen's version is, I'm not saying it's wrong. Of course, you can study this, and people have studied this, but they don't get much along this line. But now they say, okay, he says, you have to divide by the kernel. So you have to exclude the kernel of the character. This is kind of more natural. I mean, there are various reasons. I will not tell you why, but so if you think about the quotient and the normal group structure, if you define things the way, it's a lot nicer than this one. But I will not go into detail. But of course, co-degree is something people have studied. Of course, they have this conjecture of using co-degree to characterize simple group, and which is almost done recently by results. I mean, my students have done some work, right? But I think Tip also started to work on this, and they claim they've almost finished, except for some classical simple group of Lie type they haven't done yet, but I would say they probably will finish in a year or so. But anyway, so Liu and I said, is there a way to characterize the co-degree version? Of course, co-degree is a group invariant. You can talk about the prime graph of co-degrees. So I think Liu and I, the paper has been posted on arXiv for like maybe one year, but the paper hasn't been published yet. But I guess it might get accepted soon, but I'm not sure. But I think what we did is the prime co-degree version of prime graphs, we kind of more or less just recover all the previous characterization of the, we did it for solvable groups, and meta neopotent and some other thing. I mean, this is kind of not too hard because you have some results done on the prime graph version. I mean, the element order version. So I think what I can tell you is that one direction is you can just use what we know about. Yeah, I think from one direction, because of there are some nice relation between co-degree and element order. So this relation between co-degree and element order is discovered by Chen and some other people, but basically you know that one graph is just a subgraph of the other. So one direction is easy. You just say, okay, if you have a prime graph co-degree, it must satisfy these conditions. Of course, the only thing you need to do is you have to, for everything here, you have to construct a graph that satisfies. I mean, again, the construction is also the same, but of course, they're a little bit different because once you've done the construction, you have to prove that it is that one. Of course, the calculation of the prime graph for co-degree and the element order is slightly different. So you have to do some extra work to justify that. But I guess I would just say I just use the idea of these old papers to get these as a byproduct. So I guess my talk, I think that's time. I would just stop here.
Okay, thank you very much for your talk. Are there any questions to the speaker? Natalia.
Hi, thank you very much for your talk. I have a question about your previous results on groups whose Greenberg-Kegel prime graphs, complements of prime graphs are bipartite.
Oh, yes.
Your previous result.
Oh, okay. Yes. What's the question?
The question is, what's the construction of this square-free group? Really, 5 years ago, me and Ilya Gashkov have investigated Greenberg-Kegel graphs of almost simple groups. And with connection of this result, we have provided a construction of a group for each complement of bipartite graph, and for each its labeling by primes. We have constructed an example of a meta-nilpotent group with exactly whose Greenberg-Kegel graph is exactly equal to a given graph with a given labeling for any labeling of any complement of bipartite graph. Possible this construction in partial cases, possible this gives a similar construction of square-free meta-nilpotent groups whose Greenberg-Kegel graphs are complements to bipartite, but I'm not sure that this is the similar construction as yours. Possible you have provided better constructions.
Oh, I'm not aware of your result, but I guess, I mean, we will have a look. I don't know. So you say
let me write you by email. Let me write you by email.
Okay, so are you saying this work is done? Like, I don't know.
It was published about 5 years ago. I will find this paper and send you by email.
Oh, so you say this, the result about the square-free is you've already done it. I'm not.
I think that if you have a graph which is a complement to bipartite, with our construction, you can find a labeling such that this labeling, there is a square free meta-nilpotent group with Greenberg graph of this labeling. However, if you miss the condition of square free group, for any labeling, you can construct a meta-nilpotent group whose Greenberg graph is a complement to a given bipartite graph.
Oh, I see. So I guess that's okay. I see. Okay, I will look at your paper, but that, yeah, that's interesting because Thomas probably he's not aware of this result anyway.
I assume that you have provided another construction. I think that you have another construction.
Okay.
And possibly your construction is more simple.
Oh, I see. Okay.